packet. So on the cover, you can see that this is an example of an exponential growth function. There are three different functions that are on here that are growing exponentially, and they grow at a fast rate. So we will see how graphs increase rapidly or they stretch vertically pretty quickly. There are a lot of applications, real life applications to um, things outside in the world that grow exponentially. The rate of the coronavirus when it first started last March grew exponentially, and then it kind of bounced back and continued to grow exponentially this past fall. It's now on its downward curve, but that would be a very quick real life application of an exponential growth function. So we are going to start the section first looking at an exponential growth function, and this is a form, a special form. A function we now know is in that f of x notation. And the part that makes it exponential is the location of the variable. So our variable is now an exponent. So ab to the power of x. So that location of the x, last chapter was underneath a radical. Now that x is as an exponent. So wherever the x is located or what's being done to x changes the type of function that we are talking about. So a in this case, just a couple of things. A cannot be equal to 0 because if it was 0, then I would just have a line. And b is called the base. So that's the form of an exponential function. To make it a growth function, my a value has to be bigger than 0, meaning it has to be positive. And the b has to be greater than 1. That's going to make it grow. So an exponential growth function, the number in front is positive, and b is greater than 1. The growth factor, how fast or quickly it grows, is the b value. So I can look at an equation and know the rate that it's growing by looking at the value for b. So when we introduce a new function, we always try and think about what the original graph or the parent graph looks like. This is the most basic graph. So we did this same graph for parabolas. We did this graph for the radicals. We looked first just at the basic graph. So this is the function y equals b to the x when a would just be 1. So that's why I just have a b. And again, b is greater than 1. So this is the parent function for the exponential functions with a base of b. And you can see that the general shape of the graph is a curve. So this curve from left to right, that's how we read a graph. The graph rises from left to right. That's why it's considered an exponential growth function. It also says it's passing through the intercept at 0, 1. And then it'll always pass through the second point of 1 comma b. So if I make my x value 1, that's now the exponent. So any number to the value of 1 is the number itself. On the other side, there's a new term that we're going to talk about. It says the x-axis is an asymptote of the graph. An asymptote is a line that the graph approaches more and more closely. So an asymptote is kind of like an imaginary line or an invisible barrier. The graph will never cross this barrier, but it gets really close to this barrier. And Notability now has a dashed line option. It was part of the new update. So if you've updated Notability, you can choose now the style of your pen. And when we graph these asymptotes, we're going to be graphing them as dashed lines, dashed horizontal lines. And that dashed horizontal line is the x-axis. So that's going to be this barrier line where the graph gets closer and closer to, but it's going to just skim along this barrier line. So our graphs will have these asymptotes in them. So what do you think the domain is? Let's look at this graph from left to right. Annabelle, what does it look like the domain is of this function? What is the x doing?
Um,
So how far to the left do you think it goes?
Infinity.
Yeah, how far to the right do you think it would go?
Infinity.
Yeah, so this domain is from negative infinity to positive infinity. Nice job. And then when we look at the range, there is now this barrier at the x-axis. Well, the x-axis is 0. That's the y value of 0. And it goes up because it's growing to positive infinity. But it's never going to touch the value of 0. An exponential function can never be 0 because any number to a power is going to be a number that's above 0. So 1 squared, 1 cubed, 1 to the fourth, or 2 squared, 2 cubed, 2 to the fourth. That number will never be 0. So we place a parenthesis around that. And again, that's because this asymptote here is a number that the graph will never touch. So we're going to see if we can kind of look at the two graphs down below. We're going to graph them so that we can understand what the numbers in the equation are doing to the function. And then we're going to also state the domain and the range. So we're going to make ourselves a t-chart just like we typically would. So Ava R, usually when we make a t-chart, what 5 numbers do we generally pick for a t-chart?
Um, like whenever we do a cubed root t-chart or just like a normal t-chart.
Just a normal t-chart.
-2, -1, 0, 1, and 2.
Exactly. So you get to be normal again. You don't have to like rack your brain and think what good numbers are going to work. We're going to pick these 5 numbers. So -2, -1, 0, 1, 2. And then we're going to plug them in. And this is where I want you to use your mental math. So we have 1/4, and then we're taking 6 to the -2. After you do a couple, you'll kind of see what's happening with this. Thinking back to last chapter, remember math grows on itself. What happens when you have a negative exponent? So Brooke, what happens when you have a negative exponent?
You move it to the, like, you make it a fraction?
Yeah, you make it a fraction. So this is 1/4 times 6 to the -2, or 1/36. So 6 to the -2, Brooke said you make it into a fraction. Well, 6 squared is 36, but that negative makes it 1/36. Now I know multiplying those together might be a little tricky. Some of them won't be as large, but we're taking 1/4 times 1/36. And that is 1/128. 36 times 2 is 72. And then when I double 72, not 128. So the next one, try the same thing. See if you can fill out the rest of the t-chart. So you're taking 1/4 times 6 to the -1, which is 1/4 times 1/24. So any next negative exponent is going to make it into a fraction. Sorry. Come on, Mrs. Kane. I was giving you the answer there. 1/4 times 1/6 is 1/24. Plugging in a 0, we have 1/4 times 6 to the 0. Jaden, what is 6 to the 0?
1,
Yeah, so that makes
1/4.
1/4. And now the other ones are easier, way easier. Because now we're dealing with positive exponents. So we're taking 1/4 times 6 to the 1, 1/4 times 6 squared. So 1/4 of 6 is 6/4. We're taking 1/4 times 36. So 6/4 is 3/2. 1/4 of 36 is 9. So when we go to graph this, these first couple of numbers are really small. At -2, we're almost at 0, but not at 0. So when you draw
Okay.
your, yes,
For the -2, would it be 144?
yes,
one
yes,
thing.
yes. Well, yep. There we go. So that number is almost 0. So make it close to 0. The next one is 1/24. Make that just a little above the previous one. At 0, it's 1/4, so it should be just a little bit above that. So essentially, those are almost in a straight line. And then finally, we start growing. At 1, we're up at 3/2. And then at 2, we're all the way up at 9. And we'll just graph that up here, extending our y-axis. So that's how an exponential growth function works. It starts off with a minimal growth, and then all of a sudden you have a large number like 9. When you connect these, you're going to connect those points skimming along the x-axis and then going up vertically. So it almost is a horizontal at the x-axis. The x-axis is that asymptote that we're going to draw in as a dashed horizontal line, and that really should have been on the x-axis. There we go. And you can notice with your fractions how they're really close to 0, but they're never going to touch 0. Because if I had a -3 or a -4, they're just going to be smaller and smaller fractions. So it says determine the domain and the range. So we'll just place them underneath. Brooke, what would you say the domain is for this function?
-infinity, +infinity.
And how about the range?
Is it 1/4 and +infinity?
So what number is it going to get really, really, really close to? What's that x-axis value?
1/144.
Correct. So that's the lowest point that we have graphed. But it's going to continue to get closer and closer and closer to this horizontal line. And that horizontal line is at 0. So the way we show that it gets closer to it, like 1/144 is a really, really tiny number. So the way we show that it gets really close to a number, but it's going to continue to get smaller and smaller, we use a 0 and we put parentheses around that. So this 0 with parentheses is saying it's getting really close to 0, but it never becomes the value of 0 itself. And that's going to happen anytime you have this line here, this asymptote, where the numbers are very close to it. So we would never use the number in our t-chart because those numbers can continue to get smaller. Questions? All right, so let's see if we can do B. There's a 1/2 in front. It makes it a little better with a 1/2 than a 1/4. And we're having that value times 4 to the x. So the 4 is the base. You're going to pick the same numbers. So we have 1/2 times 4 to the -1, which is really 1/2 times 1/4. fourth. Good Lord, that's a -2. So you're taking a half times a fourth, which is an 8. The second one, we have 1/4 times 4 to the -1, which is 1. Apparently, I should just stop for today. This is 1/32. This is 1/8. Jeez. My mental skills are not very good for a Wednesday morning. So 1/2 times 4 to the -1 is 1/2 times 1/4, which is 1/8. 1/2 times 4 to the 0 is just a half because 4 to the 0 is 1. Half of 4 is 2. Half of 16 is 8. So again, when you graph that first one, 1/32 is really close to 0. 1/8 is only slightly above that. A half is in the middle. And then I start to grow really quickly. And that's the part of the exponential growth function. So it increases rapidly. We call that exponentially. And I'm going to draw in that area where the numbers are just increasing by a minimal value. And that value is the asymptote at the x-axis. And you can tell that's happening because these numbers are small. They're really close together. And they're going to continue if I go to the left to get smaller. The domain will always be -infinity to +infinity, no matter what. That's going to be our domain. The range is wherever it looks like those numbers are kind of becoming horizontal. And in this case, it's that 0 because it's the x-axis. So again, I wouldn't use the number 1/32 because it's going to get smaller and smaller, but it'll never become the value of 0. The fractions just get really, really, really small in values. Are there questions on graphing them? So we are going to graph 2 more functions, and those 2 functions are going to have translations. Translations mean the functions we have above are going to move. They're going to shift left or right, or they're going to shift up and down. So it says to graph the function in the form y equals ab to the x minus h plus k. Notice that h and k are in these problems just like they were last chapter. They were the same in chapter 4 and in chapter 5. It says begin by stretching the graph of y equals ab to the x. That's the graph that we would have drawn right here. So we have an a of 1/4, we have a b of 6, or we have an a of 1/2, we have a b of 4. So you begin by graphing that. Then you translate the graph horizontally by h units and vertically by k units. So if you look at the graph for example 2a, we're going to try and graph this equation. We have y equals 2 times 3 to the x minus 2 and then minus 2. To graph this, we're actually going to graph 2 functions. The first function we're going to graph would be the basic function without the shift. So I'm going to graph the 2 times the 3 and then just to the x. So right now we are ignoring the -2 and the -2. We're going to ignore that for a moment. So I'd like you to make a t-chart just like we did above. Picking those same numbers. So we have 2 times 3 to the -2, which is really 2 times 1/9. The ones with the negative exponents are a little more tricky to do. So Ella, the y values here, 2 times 1/9, what does that give you, Ella?
2/9.
And then what do you have?
2/3. 2, 6, and 18.
Nice, good job. So you can see that last number got big really quick. So we are going to graph this function. Pick a color, graph it, whatever color you want to use. I'm going to stick with, I guess, purple for now. So 2/9, 2/3. And then we'll graph the 6. We won't graph the 2 to the 18. So I can see that my graph is going horizontal on the left. And then as it goes to the right, it increases. So that's just like we did above. Same exact thing. The next part, we are going to translate this. So in the last chapter, we talked about h and k. This is x minus h. Here is plus k. H is +2, k is -2. Remember, the h is just the number sitting there because the equation is x minus. The directions say that h is a horizontal shift. So if it's +2, it means it's shifting to the right by 2 units. That's a horizontal shift. K, it says, is vertically. So I'm shifting vertically by k units. Well, it's negative, so we're going down. So h is left and right, k is up and down. I'm getting the h and the k from the equation the same way we did in the last chapter. What we're going to do is we're going to take each one of our points and shift them. So my first point, I'm going right 2, down 2. So I'm starting on the right side, that upper point. That's where my new location would be. Right 2, down 2. My next one moves right 2, down 2. And that's my new point. So each one of your points, you're moving right 2 and down 2. So right 2, down 2. And one more time, right 2, down 2. Your graph should have the same shape, the same steepness, it just has shifted. Questions on that? Please ask if you have questions. So if you look at the portion that now is horizontal on the left side, that left side is kind of like a horizontal, just going to be skimming along to the left in that format. Right underneath that is where this asymptote is located. So now that asymptote is down at 2 on the y-axis. You're going to find that by seeing where the graph is going horizontally. Where does it look like it's kind of making a flat line? So Gabby Snyder, can you tell me what the domain is for this graph?
-infinity to +infinity.
Yeah. And then if you look at the range, Gabby, where is that dashed line at?
-2.
And then how high does the graph go?
+infinity.
Yeah. Both of those get parentheses as well. So there will be no brackets in these equations when we look at the domain and the range. It'll get close to -2, but it'll never touch it. So we're going to do one more graph, just so you can kind of get an idea of that shifting of the graph. Faith, can you tell me just the basic equation that we're going to graph? So up above, we just did y equals 2 times 3 to the x. What would the basic graph be, or equation be here, Faith, that we will try and graph?
2 times 4 to the x.
Yeah, 2 times 4 to the x. So make yourself a little t-chart. Pick the same x's, plug them in to find y. So again, you're just using 2 times 4 to the x. And that last one, you're going to see that's going to get big quick, that it might not be easy to graph sometimes. So this is 2 times 1/16, 2 times 1/4, and then the other ones are a lot easier. When you place them in your t-chart, reduce them. So 2/16 is 1/8. 2/4 is 1/2. 2 times 1 is just 2. 2 times 4 is 8. And then 2 times 16 is 32. So see if you can graph these. Again, you're not going to graph 2 and 32. But I can squeeze in that 1 and 8. So it gets horizontal on the left. Anytime you start to see that curve, that's why those negative numbers are really important for our x. That curve shows you where the graph goes horizontally. And then if we look at our h and k, so this is x minus h plus k. Grace, what would the h and k values be in this problem?
H would be -1
Yeah.
and K would be -3.
So how is the -1 going to move the graph?
It would go to the left and the -3 would go down.
Nice job. Good. So starting with your point, left 1, down 3. The next one, left 1, down 3. And that last set of points are really close to the bottom of the graph and to the far left of our graph. So try and make it horizontal with those 2 points that are at the left. So left 1, down 3. Questions with that? We're going to draw in that dashed horizontal line. And then we're going to write the domain, -infinity to +infinity. And the range is at that dashed horizontal line, which is -3, and then to +infinity. So your K value controls the range. That's an easy thing to kind of think about. Whatever your K is the value of the range. That's where that asymptote is going to be located. Are there any questions? So the other thing that we're going to look at is the definition of an exponential growth model. Remember, a model is really kind of modeling a real life application. So how can I take something out in the world and pull it together from math? So it says a real life quantity increases by a fixed percent each year or over a period of time. The amount y of the quantity after t years can be modeled by the equation. So our equation for an exponential growth model is y equals a 1 plus r to the exponent of t. The a is your initial amount. That's what you begin with. So what is our beginning amount? R is the percent increase but it is expressed as a decimal. T is going to represent time. So inside the parentheses, the reason it's 1 plus is because I'm starting with 100% of my population. So I have 100% of rabbits in my yard. And then that percentage increases. So beyond 100%, how much further does it increase? And that's why you're adding the rate to 1. Because to increase something, you have to take your 100% and go beyond it. So in example 3, we're going to use this model. And we're talking about buffalo. In the past 12 years, an initial population of 38 buffalo in a state park grew by about 7% per year. So if I go back and read it again, in the last 12 years, an initial population of 38 buffalo grew by 7% a year. Write an exponential growth model giving the number of n buffalo after t years. How many buffalo were in the park after 7 years? So the 12 years is just kind of saying that's the amount of time that this percent kind of was gathered. So we're not going to use the 12 in the equation, but they're saying that over the past 12 years, 7% was the percentage of growth. We are going to look at that 38 because 38, it says, is the initial population. So when we go to write our equation, it wants us to use n instead of y. So we'll use n instead of y. So the number of buffalo would be equal to the initial amount. Well, we started with 38. It grew by 7% every year. Well, 7% is our R value, so that's R, but we need to write it as a decimal, and that's 0.07. And then it says T for years. We're making an equation right now, so we're going to plug in T for time. So we have 38. 1 plus 0.07 is 1.07, and then to the T power. That would be my equation. So 38 buffalo, 7%, 0.07 is our rate. How many buffalo were in the park after 7 years? So you will need a calculator for this. 1.07, and then you're taking that to the power of 7. So see if you can plug that in your calculator. And it says about how many buffalo were present. So about how many buffalo. So plug that in your calculator about how many buffalo were present in the park. Jordan, about how many buffalo did you get?
I kind of got like a weird number, so I'm still trying to figure it out.
Okay, so in your calculator, if you type it in exactly as it's written, so take 38, in parentheses, do 1.07, end your parenthesis, and then use the caret button and the 7.
Okay, I got 61 buffalo.
That's it. Yep, nice. You got it. Good. Questions? So we're going to skip the graph part. We did enough graphing. The last part here that I want to give you is a second formula that is called a compound interest formula. When you invest money, you earn interest. When you buy a house, when you buy a car, when you take out a loan, you pay interest. Interest is calculated with an interest formula. Makes sense. You got to have a formula to calculate interest. So this formula starts with a big A, and that's the amount. P is your principal, and I'll give you a little definition on the side. And then we have 1 plus R divided by N, and then NT. There's a lot of stuff there. And I know it is 8:05. I just want to give you these terms here so you know what you're looking at. A is the end amount, what you end with. P is your beginning amount, or we call that the principal. R is the rate. R will always be rate as a decimal. T is time. And then N is the number of compoundings. So I believe you have one problem in your homework that is using this, and unfortunately we did not get to it completely. That's the bummer about learning virtually. Look in your book, your honors students, see if you can try and read through the question. It's a plug and chug. You just have to know where the numbers go in the equation. Try your best on that problem. The rest of it we did get to cover, we got to talk about. And as I said, tomorrow we're going to do more of these problems. And then on Friday, we'll kind of review the first 2 sections of this chapter. So have a fantastic day. If you have questions, please feel free to stay on and ask any questions that you have, but have a great day otherwise.